In this video, I would like to go through several examples of how KLEE reacts when it executes a bunch of different applications that each have memory corruption vulnerabilities. So I have 4 examples here, and each of the examples has a different type of memory corruption vulnerability, and then we are going to see how KLEE reacts when it analyzes each of the programs. So let's start with the first example here. So we have our main function. Inside the main function, we have a local array, and we make the 10 bytes of the local array symbolic, and then we assign the last byte in the array. We assume that to be a null terminator. Following that, so we create an array of 10 bytes where the 9 first bytes in the array are symbolic, and the last one is assumed to be a null terminator. Then we call the test1 function with our array as an argument. Inside the test1 function, we first declare a local variable I equals 5, and after then we do a string compare on the buffer and see if it is bug with an exclamation mark. If indeed that's the case, then we add another 20 to the local I variable. After that, we return the ith element inside the global array, and global R here is declared to be an array of 10 elements where we have the numbers 0, 2, and including 9. So the bug here is that if the buffer is equal to bug with an exclamation mark, then we are going to return the integer at the index number 25 in the global R. But since the array is only 10 elements long, it will be a memory out of bounds. So let's see how KLEE reacts to that. So over here we have the program. And again, this is inside the KLEE Docker image that I showed how to install and use in the previous videos. So it's the exact same program as on the right, except we have a comment here. Let's remove that. Okay, so we are going to compile the program and extract the LLVM bitcode, similar to what we have done in the past. And we will also include the -g flag, which compiles the program with debugging symbols. And this is going to be useful when we will analyze the bugs found by KLEE later. So we got our bitcode ex1.bc, and we got also a few warnings here with implicit declaration of various KLEE functions. But in this case, we don't care about those because the functions will be defined and they will be implemented inside of our KLEE environment when we start analyzing the BC file in KLEE. Okay, so we execute KLEE and to analyze our example, and we will use the UC libc version of libc with KLEE because we have a string compare function here. Okay, so this is the report from KLEE. It found 6 different execution paths, and then it also found reports were found at memory out of bound at line number 13 inside of exe1.c. We can see here that line 13 is indeed the memory access operation that will be triggered the bug. Trigger the bug. So if we get into our directory with the artifacts from the KLEE result, then we can see that we have here the 6 different test cases, and we also have the a test 00003.pointer.r, which is the error report produced by KLEE for the error case that was found. So if we look at that error report, then we see a stack trace of where the error occurred, and again we get line number 13 inside of our program, which is indeed the case. We also get the line number inside of the assembly.dll. So if we look at line number 578 inside of the LLVM IR that was analyzed by KLEE, then we see here the LLVM load instruction that resulted in the memory out of bounds. So here array index, the local variable array index will hold an address in memory that is outside the bounds of any memory object allocated in the memory address space. If we look a little bit more at the error report, we can also see that KLEE even gives us the address where the error, the address that was trying to be accessed when the error happened. And that's about the information that the error report gives us. We can then see what was indeed the value of the symbolic buffer that was needed to trigger the bug, which is the same number ktest file as the ptr.error file. And we can see that indeed the data that was needed to, the values of the buffer that was needed to trigger the bug was indeed bug with exclamation marks. So this was an example of where KLEE successfully detected a memory out of bounds for a global buffer, and that is KLEE was able to detect a global buffer overflow, and also gave us valuable insights such as where the error occurred. Okay, so let's look at the second example of vulnerable application. So this is our second example, and the main function is very similar to, is the exact same as the previous example. We have a local variable of a 10-byte array, and we make all 10 bytes of the array a symbolic, and then we set the last byte in the array to be a null terminator, and then we call into our test2 function with the symbolic array. Inside the test2 function, we dynamically allocate an array of 10 bytes, and after that we set the values of the array to be 0 to and including 9. We then declare a local variable called I equals 5, and then we do a string compare on the symbolic buffer with bug exclamation mark, and if indeed the buffer is similar to bug with an exclamation mark, then I plus equals 20. After that, we declare a local variable called return value to be the integer in the dynamically allocated memory index I, which means that we access the given integer that is located in the array here. However, if I is equal to 25, which it will be if this line of code is executed, then we will have here an memory access at index number 25 in the dynamically allocated memory. Since the dynamically allocated memory only holds 10 elements, we will indeed have a buffer overflow here. However, in comparison to our previous example, this buffer overflow will be in a dynamically allocated memory rather than a global buffer overflow. So that's the key difference between this bug and the previous bug, that this is a buffer overflow but on dynamically allocated memory rather than global memory. So let's see how KLEE reacts to that. So let's see here that this is indeed the program, and it is the exact same as the one on the right side. And we compile it in our usual way with debug symbols, and we want the LLVM IR. And again, we get a couple of warnings with implicit declaration of various KLEE functions, and we don't care about that since they will exist in our KLEE execution environment. And then we call KLEE on the bitcode here, and we use uclibc as our libc, and we run KLEE on it. So here we can see KLEE again catches a memory out of bounds, and it tells us that the error occurs at line 25, and line 25 here is the exact line where the memory out of bounds access happened. KLEE also indicates that it found 6 different execution paths, which is similar to before. So let's see what KLEE has produced in its artifact directory. So here we see that the error report is right here. So let's try and read that. And we can see that again it shows us the address that was trying to be accessed, which was is outside of any object allocated in memory. And we also have the specific line where the error occurred. We have the whole stack trace. We also have the line in the assembly.ll file, and we can try to access that. Is 615. And it's very similar to before. We have a load instruction here, and it's again this that will hold this local VM variable that will hold memory, that will hold the address of that will hold an address which is an address that points to something that was not allocated in the KLEE memory space. And so here we can see that KLEE correctly identifies memory out of bounds on a dynamically allocated memory rather than global memory. So that's another type of vulnerability that you can find with KLEE. Okay, so let's look at our third example. So in a third example, we have the exact same main function as before, but inside the test3 function, we declare a local variable I equals to 1. We then do our usual string compare on the buffer, and if indeed the buffer is bug exclamation mark, then we assign I equals to 3. And before I do that, I will show one thing that I didn't show previously, which was that indeed where the PTR error occurred, indeed the bug was the test case that triggered that was indeed the one with bug exclamation mark. I don't think I showed that, so let me just show quickly that indeed it was the correct test case that where KLEE found the memory corruption bug to exist. Okay, so let's go back to this example. So here we, if the buffer is equal to bug exclamation mark, then we assign I to be equal to 3. And after that, we declare a local character C to be the referenced value of the string at the ith place in the global string array. So in the global string array, we have three strings: string 1, string 2, and string 3. And then we also have a null value at as the fourth element in the array. So what C will be set to is, if I equals to 1, then it will be the first character in the, if I is equal to 0, then C will be equal to the first character in the 0th string in the global string array. And if I is equal to 1, then C will be equal to S, which is the first character in the second string in the global string array. And if I is equal to 2, then C will be set to the first character in the third string of the global string array. But if I is equal to 3, which is the case where our symbolic buffer is equal to bug exclamation mark, then C will be set to the first character of the string null. But since this is a null value, we will not be able to dereference that, since, well, we will be trying to dereference 0. And therefore, we will now see a null dereference in case I equals to 3, which is kind of similar to before, in that we are trying to access memory outside. We are trying to access memory at some ill-defined memory address. But at the same time, this is a very common one where we have a null dereference, so the address that we will be trying to dereference is 0. Okay, so let's see how KLEE reacts to that. And we can see here that indeed the program on the left is the exact same program as on the right. Okay, so we compile it our usual way. And again, we get various warnings for implicit function declarations, but that doesn't matter since they will exist inside the KLEE execution environment. And then we execute KLEE on the resulting bitcode. We can see here is the resulting bitcode. and we execute KLEE on it with libc set to uclibc. And again, we get 6 different execution paths. We get a memory out of bounds at line number 20. And at line number 20 is the exact place where our invalid memory access is. So let's see a little bit more inside the artifacts produced by KLEE. So first and foremost, the error case where the test case where the error occurs is test case number 4. So if we check what the value of the buffer is in that test case, then we can see that it is indeed bug with exclamation mark. Now, if we look at the report, the error report itself, we can see that we get indeed this is a memory out of bound error, and we get the specific line, we get the whole stack trace as well, and we get the line inside of assembly.ll. But here we also get, similar to before, we get the value of the address that was trying to be accessed, but here we get the value 0. So although KLEE doesn't actually write it to us, tell us that this is a null pointer dereference, it's very clear from the fact that the address is 0. And we can then easily tell that, well, we were trying to dereference or access. In the end, dereference is access of memory, and therefore we were trying to access the value at, we were trying to access the bytes at the address 0. So that corresponds to a null dereference. And again, we can see the line inside of the assembly.ll file. And again, it is a load instruction, and this load instruction corresponds to the value that is trying to dereference the address inside of here. Okay, so that was the third example of how KLEE reacts to a null pointer dereference. Let's look at our fourth example. Our fourth example is a little bit different in the sense that we have the exact same main function. We declare our local array, and then we make the bytes of the array symbolic, and we set the last byte in the array to be a null terminator, and then we call into test 4. In test 4, we allocate a buffer of 10 byte on the heap, and then afterwards we do a string compare on the buffer here with the value bug as before. And if indeed the buffer is equal to bug with exclamation mark, then we free the variable we have just dynamically allocated up here. Afterwards, we then free the variable again. So in this case, so this example is a case of a double free. So let's see how KLEE reacts to that. We have over here the exact same program. We have our double free here, and we compile it in the regular way, and we get the implicit declarations warnings. We don't care about those. And we have the BC code here, the ALLVM bit code, and we call KLEE on it using libc equals to userlibc and ex4.bc. Okay, so we get a similar output, quite similar output to before. We have 6 different test cases, and we see, but now we see a different type of error. Specifically, we see a memory error, invalid pointer inside something that is related to free. We get the line number here, which is line number 12, where the error occurs, and indeed on line 12 we have the call to free that triggers the double free. If we go into the artifacts produced by KLEE, we can see the test case that triggered the bug is test case number 3. So if we check what is the value of the symbolic buffer at that point, we can see that the value is bug in capital letters with exclamation mark. Indeed, that is the one that triggers the bug. We can then see the error report produced, and we get similar to before, we get the stack trace, we get the line where it occurred. We have here a short description of the error. It's an invalid pointer and it's related to free. we have the assembly line in the line number in the assembly LL. So let's see what's at that line. We can see that there is a call to free. So it is the KLEE reports this exact line where the free call is, and we can see here that it reports a given address as well, but again it tells us something, but it doesn't tell us a whole lot that that's indeed the address that was occurred. But it does show us that this is where this is the address that was causing problems. Okay, so that's it for this video. In this video I showed 4 examples, the first here, the second and the third and the fourth, of how KLEE reacts to various different memory corruption vulnerabilities. 2 of them, the first one was a global buffer overflow. The second was a heap overflow, so it was an overflow on a buffer overflow on dynamically allocated memory. And the third example was a null dereference, and the fourth example was a double free. And KLEE was able to produce quite informative input for each of the different bugs, and it also showed us nice stack traces and even more information for each of the bugs. So that's it for now. Thank you for watching the video.